All right, so today, since it's the first lecture, we're doing some introductory stuff. We've got this to go over and some introductory problem solving. Ooh, and that thing just turned right over. Better. There we go. Now, on this syllabus, let's go over some basic stuff. Some of you are going to be doctors. All of you have experienced a doctor or a dentist. And what happens when the doctor says, you may feel some slight discomfort? What happens? You feel pain. Dr. Eschenberg says at the beginning of the semester, this is going to hurt. Physics 213 and 214, if you choose to do so, is a very difficult task. You are learning an entire semester of physics in 28 days. That is a very difficult thing to do. My recommendation to you is, if you're taking organic chemistry and physics over the summer and you're able to pull that off, more power to you. But what I believe in, you got to choose one or the other. In the course of the next week, you'll take your first test and we will figure out whether or not you're going to be here for the summer. If you drop the summer, that's fine. There's no great shame in dropping a summer class because it's a lot of material in a short amount of time. The downside to that is, and this is where we have some golden opportunity, this is the last time I'm teaching 213 at Ole Miss. It was a visiting faculty position. Visiting faculty positions are not tenured. They end eventually, and so mine did. This gives us one last opportunity to record what this class is, what we do, what it means, what I want you to get out of it. And it's basically boot camp. For 4 weeks, this is what we're going to do. We're going to do physics. I suggest that you live in the tutoring room. We're going to have tutors there available all the time. When you're not in lab, you should be in the tutoring room. When you're not in Lewis Hall, you should be asleep. It's basic. Just face the fact, admit it to yourself that you're not going to have a life for the next 4 weeks. It is not a pleasant experience. However, the students who do really well in my class over the summer, the ones who get the B's and the A's, when they come to me for a letter of recommendation for med school, for dental school, for optometry school, for all those things, one of the things that I mentioned in the letter is that if you do well in this class, that means a lot to me because you're able to squeeze in a whole lot of information and understand it in a small amount of time. And for a person to get an A in the summer, you're in my top grade of students. And so I really like that. In this class, we have set test dates. These test dates are in stone. There is a particular style of pedagogy that I believe in. I call it rush and review. Effectively, what we're going to do is we're going to take an entire test's worth of material and initially cover it in 3 days and assign homework for it over those 3 days. Then for the 4th and 5th day, we do review. I believe it takes time for concrete to set. So for 2 days, we're basically hashing out those problems. On day 6, we test. Lather, rinse, repeat 3 times. We take a review day for the final, and then we take the final. It's a lot of information in a short amount of time, but if we set to this procedure, then things will go well. The final has been set. It's in here June 26th from noon to 3. Homework. Homework is the bane of my existence. We do have 3 graders over the summer, and that's a good thing. Typically we have 2. Homework is written. I do not believe in online homework. I believe that there is a disconnect between the homework that you're assigned and the tests that you're given. If you do mastering physics and then you write your own test, the student isn't prepared for what the tests usually are. And so what I tend to do is think of my homework sets as mock tests. They're difficult tests. One of my beliefs is it is much better to sweat in practice than bleed in combat. The homeworks are meant to be hard, to push the boundaries so that by the time you get to the test, you go, well, that wasn't that bad. So that's my philosophy on homework. It's all written. Turn it in. Turn as much as you can in. The homework, when you get it back, will have a number, typically like 4, 5, or 6 out of 6. What I do is I tell the graders to pick 3 problems I pick the 3 problems at random, kinda. And then they are given a 2-point scale per problem. So 3 problems, 2.6. That's where the 6 comes from. If the homework looks like, that particular problem looks like less than 50% of it has been done, or I'm sorry, less than 25% has been done, so it's blank or you're trying to con the grader, you get 0 points. If you participate between 25 and 75% correct, it's 1 point. If it's greater than 75%, it's 2. That's to prevent the grader from just like slamming you by taking, like you dropped a sign or something. What we do, if I had it my way, let's talk. If I did it my way, I would have the homework worth nothing. But what would happen if the homework was worth nothing? Well, the test, that's a practical matter. What I'm looking for is what happens in reality. Nobody does it. So in the end, no one does the homework, the tests begin to lag behind. So what I do is I make it worth a little bit, just to keep you guys honest. 10% isn't that much. It's not going to destroy your world. If you forget one problem set, that's fine. My philosophy on written homework, you will notice, let me put this up. This is the map of Lewis Hall. I'm here. We're actually technically, physically, I'm right here. But down the hall towards the bathrooms in the back, this is my office, and these are the drop boxes. When you turn in homework, you can either give it to me in class or put it in the box. The box will be this large 1 foot by 2 foot box wrapped in neon orange tape with the words Dropbox on it. And if you stand in this office and you actually ask me, where is the box? We will play Find the Box game, which means you will turn around once in that room, and if you cannot find the box by the time you turn around to face me again, I failed. Keeps things simple. This box could be seen from space. So for you to only be 10 feet away from it and ask where it is, it disturbs me a little bit. Makes me wonder. As I said, this is here. This is the lab. So if we leave here, turn left, go to the end of the hall, this room, the door on the left, is your lab room. That's where you go to lab. Go to lab. Go to lab. When in doubt, go to lab. There is a schedule. If it's not on here, it's on the physics lab website. Oh, here. Oh, it didn't show up. Well, this is helpful. This in heavy black are the dates of the labs. I'll get a better list. But when you go to lab this afternoon, and yes, there is lab this afternoon, the TAs will give you the schedule. We do not meet every afternoon. At most, 3 afternoons a week. I think there's a week in 214 where it's 4, but that's just one time. So it's a little bit of a floating, it's not always Monday, Tuesdays, Wednesdays, but rest assured, I don't think we ever have a lab on Friday afternoon. So it's not that big of a deal. The overall grades, I do an expanded plus-minus system. So an 88 technically in my world is an A-. The labs are an ABC system where 90 is an A, 80 is a B. It's a conventional thing. Personally, I don't care about numbers. I'm fine with two different grading schemes. I'm fine with the fact that the lab is an ABC system and we're plus-minus. Why? Because I place way more weight on the class than the lab. Class is worth 3 times as much. You should put in 3 times the effort in class. If you're thinking you're overworking in lab, then slow down. You're doing too much. This is the link for the lab, so it has the schedule there. The rest of this are just a whole bunch of facts, questions, all sorts of stuff. I'll hit the highlights. If you have any detailed questions about the syllabus, let me know. This is the book. This is the combined 2-volume set. There is an approved University of Mississippi copy where there's a copy for 213 and a copy for 214. I think it's a good idea to buy the book. I think it's a great idea. Do we all understand what I'm trying to say here? What I did is I spent a year with the publishing company. Originally, I wasn't a big fan of using the book, and then the publishing company came to me and said, well, what we'll do is we'll make a deal that will effectively cut the price of the book by 50%. So we made it a loose leaf copy. We made it so that it printed only the chapters that we were going to cover. I had to get approval from 2 of the other professors. And then the book shipped to the bookstore. And the students came back and told me what price they had set. They didn't cut it by 50%. They increased it by 15%. Needless to say, no one hurts my students. I'm the only one allowed to hurt my students. So what I did is I changed the book from required to recommended. Basically throwing the bookstore under the bus and sinking them with 400 copies of these books. So if you find one in a ditch, more power to you. You can pick it up and use it then. If you find it used, great. But we do not, if we do problems out of the book, I'm going to take them out of the book myself and I'm going to put it in my problem sets. For the first problem set, it is, I'll probably end up printing the problem sets. They're not that big of a deal. When you've got 300 students, it's a big deal. But the problem sets, in addition to being handed out, will be available online. So you can, most of the stuff will be online. In fact, here's another thing that's different about me. A lot of professors hold back on their tests. They don't want their tests out in the wilderness, roaming around for you to look at. I call that studying. So what you guys are going to get in the next day or so, I'm going to put it on Blackboard, are copies of the 213 from last fall, last summer, last spring, the ones that were recently given, so that you can take a look at it and see what you've, or what's expected of you. Kind of my universal theory of you as a physics student. Many of you who have never taken, back it up, take 2. Many of you have never taken physics before. Never had it in high school. I actually prefer this. You're a blank slate. A lot of you who have taken physics had a really bad teacher. Horrible. You have no knowledge of problem solving, physics, trigonometry, algebra. I accept you for who you are. A lot of professors expect you to understand this information right off the bat. Why are you here in 213? Because you've never had it before. I understand this and I expect this. But what I want from you, give me your effort, give me your faith that I'm not here to fail you, and we'll all come out of this alive. So let's get started. The first thing I want to talk about, it's kind of a practical matter. You'll be doing the measurement lab this afternoon. We're going to run through this really quick. This is a vernier caliper. Now, people talk about how you're not allowed to bring weapons like guns and stuff on campus or whatever for a safer campus. You can kill somebody with this in like 3 different ways. Let me show you how. The first way is to measure typically width. These things right here, and in fact, let me show you the prongs. Whoa. All right. So what you notice, the first thing that I want you to teach, or I want to teach you about, is that there are 2 regions in the tongs. There is, doesn't really matter that it's not focused. There's this region that extends out from this region. So see how there's like a little lip right here, and then it gets a little bit thicker on this prong. This is where you measure your widths. So to measure the width of this ruler, you put it like this. You don't put it in like that. That will give you an inaccurate measurement. So you have to pull it out and measure it at the edge. The other ways, so that measures the width of stuff. Now say that there was a hole, like say of this lid, and I wanted to measure the inside width of the lid. Well, that's what this is for. You put those in and you spread them out, and then that will give you the width, inside width. Now there's depth of hole. That's where this thing comes in. You put it so that this bottom of the main ruler rests on top of the hole. And then this point rests at the bottom. And then you've got your depth. So this thing can measure width from the outside, width from the inside, and depth. So it's a very useful instrument. Now let's figure this out. There we go. Now I'm going to adjust this so I get the reading that I want. The ruler, or the vernier caliper, reads in both metric and in imperial units. Without the markers, you can kind of tell which one is which. 6, 7, 8, 9, 10, those are in centimeters. See how this goes 2, 4, 6, 8, and then big 3, 2, 4, 6, 8, big 4, those are in inches. Physics of 213, we use the metric system. So we're going to use feet, miles, and stuff for standard conversions. But in terms of your day-to-day life, in 213, it's all metric. The first thing you look for, now what's really freaky, some of them, the millimeters are on the bottom and the inches are on the top. And some students come to me and go, well, you didn't teach us what would happen if the millimeters were on the bottom. And I'm like, really? That's what I have to put up with? If the millimeters are on the bottom, you do the same thing. It doesn't really matter. You don't always read the top, but you do read millimeters. The first thing you gotta do is ignore this edge right here. That does nothing for the measurement. But what you are doing is you're looking for, not you. Now for me, I'm blind. So what I typically do is I bring my iPhone in, I take the camera and I zoom it so that I can look at it, because I can't see this normally. First thing you want to do is you want to look at that, the 0. Well, where is the 0? Well, if that's 7 centimeters or 70 millimeters, and that's 8 or 80 millimeters, that's 1, 2, 3, 4, 5. So it's 75 millimeters at least. 70, 1, 2, 3, 4, and 5. If that 0 was to the left of this line, it would be 74. If the 0 was over here, it would be 78. So the first thing you need to do is look over and see where that 0 is. And I'm repeating myself because you guys will measure this and come to me, and then I will present you to the class for group scolding. So the next thing you want to do is you got to find out what the nearest fraction of a millimeter you're dealing with. Over here, let's talk about that for a moment. Over here we have something called 0.005. That's kind of hard. 0.005 or 0.05. That's the resolution of the vernier caliper. It only measures in increments of 0.05. So you could have 72.05 millimeters, 72.10 millimeters, but you cannot have 72.12 millimeters. The last digit always has to be either a 0 or a 5. So let's get back to this. Now this is where there's a little bit of artistic freedom. And really, let's look at this line right here. This line doesn't line up with anything. This line really doesn't line up with anything. But over here, I would say that too does line up pretty well with these millimeter notches. What this is set up to do is to give you those last 2 digits. If this was the one that lined up, it would be 0.05, 0.10, 0.15, 0.20, 0.25. I would say either this one lines up fine, so it's 75.15, or I would say that this lines up very well. So you could say 75.20 millimeters. And so that's how you read a vernier caliper. I'm not picky. I keep saying I'm not a big fan of numbers. I'm more interested in the understanding of the physics and how the equations work. If you said 0.20, 0.25, 0.15, I won't sweat it. It's not that big of a deal. If you said 0.45, we now have a situation. You're not really reading it right. So what we're going to do before we really start physics is I'm going to give you So what are the first 2 digits? And you can speak up.
55.
55? All right. Congratulations. You're the first victim of group ridicule. What did he do wrong? You measured from the edge.
That's on purpose as a teacher.
Okay. I'm sorry, are we doing an exchange program with state? No?
I did transfer.
You did transfer. I could tell. Where should I look first? The 0. The 0 is between what and what? 57 to 58. So the answer is 57. The 0 is to the left of the 58th millimeter mark. So it can't be 58 or greater. It has to be between 57 and 58. Where do the next lines line up? The 6. I would say 6 or 6.5. Either one would be fine. So the answer is 57.60 or 57.65. And that is the way you read a vertical calendar. Some of the TAs mess it up, so that's why I teach in my class. All right. Now first half hour. One, about this class, we do not break. We got to cover a whole semester of physics, so we're not going to take a 10-minute break. We will end promptly at 11:50. I start my classes on time. They end on time, if not a little earlier. If you need to go to the restroom during the class, it's not a big deal. Just get up, walk out to the bathroom, do your business, come back, everything will be fine. So occasionally, I get a journalism student in my class. And journalism students are taught to ask questions. In fact, here's a lesson. I asked the chair of the department what makes the difference between a good student and a great student. He said, sagely, good students have the ability to answer any question given to them. Great students have the ability to ask themselves their own questions and answer those as well. So the first thing that we got to do, I am looking for now the first thing you're going to do is realize I'm left-handed, which means everybody on that side of the room is doomed. But welcome to my world. Right-handers have been oppressing me since the start, so it's payback time. What 4 questions about these balls can you ask about them? Now, here's another thing. I believe in class participation. I understand I gotta say a lot, so you're gonna listen a lot, but occasionally I do ask questions and I expect answers. So what question can you ask of these?
What is their volume?
What is their volume? That's a too complex question.
How big are they?
Are they what?
How big are they? Or
Too complex. Looking for a more basic question.
what color are they?
Too complex.
Are they moving?
Are they moving? Too complex. Think about more like a journalist in the back.
What are they made of?
What are they made of? That's material science. Too complex. Yes. Is it what? Blue? No. And again, you repeated the question that someone else had. Another question. Yes.
What the weight of them is?
Very good. It's a little more complex than what I'd want, but I'll accept it. How much of it is there? So there could be a lot of balls here, there could be a few balls here. There could be just massive balls, there could be tiny balls. So how much of a mass are we dealing with? Now, we've dealt with velocity and volume. What's a more basic question than velocity or volume? And when I say it, you're going to go, well, of course. Crickets, crickets. And there, in fact, there are 4. Think about what a journalist would ask. Basic question. I'm only going to spend another 2 minutes, otherwise I'm starting answering. And then you all disappointed me. Huh?
What shape do they make?
That's like volume, and I'll even start answering it more. Volume, shape, dimension starts with, or the word starts with P. Or blank is it? It's not, and the P word is not in blank, but it's the, it's gonna be a long semester. Where is it? Position, yes. Now comes the two tougher questions. What other questions can you ask it? Now, one, if you ask it, I go, oh, you're very head of the class, I see. Yes. The other one is obvious. How many are there? And then the last question, and this is why I'm saying basic. When is it? Who, what, where, when, why, how? The fundamentals questions of journalists. Fundamental questions of physicists. How much of it is there? Where is it? How many are there? When is it? The world has SI units, system international, or what we would call the metric system. Then there is the imperial system, or what America uses. The imperial system is used by the United States of America, some Central African dictatorship, and a Southeast Asia country in various extents, but the majority of, or pretty much everybody else, uses SI units or metric. How much of it is there? The concept that we're talking about is mass. This table has a lot of mass. This ball has less mass. Where is it? Position, location, eventually branching off into volume, area, stuff like that. How many are there? That's called the count. 2, 24, 1 billion, 1 trillion. When is it? Time. So those 4 quantities are fundamental units. You cannot describe them as a part of anything else. Everything we study in 213 will be based off those 4 quantities. The units that we use for mass is the kilogram. Now, imperial units, you're very familiar with pounds, but pounds technically is a force. What you're using, or what you see on a scale, is a mass pound. The truest definition of mass in an imperial system, it's called a slug. But when you get on a scale and you're told, oh, you're 112 slugs, the marketing of that is not very good. Can't really sell slug. So they changed it to a mass pound, and that's what we get. For position is the meter. Imperial units, we got all sorts of descriptions. Foot, what typically is used. For the count, imperial system is the dozen. How many dozen? For SI, it is a mole. What we're familiar with in chemistry, 6.02 times 10 to the 23rd. For time, there was an experiment to use metric time, but it failed miserably. So all we get are seconds. In both, the universal unit for time is a second. Now, that doesn't take into account daylight savings time, but that's a different argument for a different day. For all of these, really on the first day, we're just easing out into the driveway. We gotta understand for mass, there are different units and different relationships between quantities of mass. We have a kilogram, and that is equal to 1,000 grams. If you've got a kilogram of stuff, you got 1,000 grams. For a pound, it's 454 grams. Also 16 ounces is the universal conversion for all this stuff. For position or length, we have 12 inches per foot, 5,280 feet per mile. We have 1,000 meters in a kilometer. Conversion is 2.54 centimeters per inch. And the last one, which I don't really, you'll have a homework problem on, but you won't be tested on it. You have 1 mile per 8 furlongs. So what is a furlong? Anybody seen the Kentucky Derby? It's a unit of length primarily used in horse racing. It's used elsewhere, but that's where it's typically used. So 8 furlongs in a mile. There is, we've done mass, position. The count, that's really simple. We don't go into dozen is 12. How I know this, I grew up on the Gulf Coast. Bottle rockets, 1 gross of bottle rockets is a dozen or 144. You have a mole, 6.02 times 10 to the 23rd. So if you had a mole of students, which is not something that I would recommend, because that would be a lot. Where would you put it? Count's really easy, and we don't really use it all that much. For time, the basics are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 for nitpickers, 365.25 days in a year. Another thing that's really interesting to talk about and just to see is pi times 10 to the 7th seconds is 1 year. About. Within like within like a percentage of accuracy. Close enough. So these are all of the basic conversions that we'll typically use. I would say that the big guys are this and even bigger is that. So those are, I mean, this is the one where you just have to know by heart. Now that we've introduced these units, there's something that we haven't really covered, well, we've not covered because we've just been working for 45 minutes, is this K and M, kilogram, kilometer. What does all this mean? In the imperial system, everything is based on these weird 12s, 5280, 12, 454 grams, 16 ounces to a pound. In the metric system, it's all base 10. I keep pushing for it. I keep asking for it. No one's decided to follow through on it. I would hope for a President Carter tried to do it and then the country resisted. We should have a units coup where we wake up and the tanks are in the streets and all the mile markers have been torn down and kilometer markers have been put up. Everything at the Walmart are now in kilograms and grams. We just need to, our generation needs to take one for the team and just make the change. Because the further we go, the harder it is to make the conversion. Now, what the core thing about the metric system is everything is base 10 So we have 1,000, million, billion, and this gets tiring. I'm going to write all these zeros down and keep track of how many zeros. So what we do is we tend to shorten it. 10 to the 3, 10 to the 6th, 10 to the 9, 10 to the 12th, 10 to the 15. So rather than having to write 15 zeros, you just write 15 to the superscript of a 10. For the really small, so this is 10 to the -1. So how many places to the right of the decimal point is it? So 1, 2, 3, 10 to the -3, 10 to the -6, 10 to the -9, 10 to the -12. We really won't go past 10 to the 12th. Yeah, we'll just keep it at that. But for here, you're familiar with 10 to the -3 or milli. So if I have a millimeter, it's 1/1000th of a meter. So when you look at that, it just seems evident. Millimeter, 1/1000 of a meter. 10 to the -6, micro. Now, milli is little m. So millimeter, meter is a little m as well, and the units are little m, little m. When I typically write it in brackets, that's to denote the units being used. Now, we've already used m right out of the bat, the little m. We're going to use big M for the big numbers. So micro, we used this. For those of you in the Greek system, you know it already. For those of you who have taken a lot of science, you've seen it. This is a mu. It looks like a mutant cursive M. It is the Greek letter for M, and it denotes 1/1,000,000th. So if I have a micrometer, It's 1/1,000,000th of a meter. Now 10 to the 9th nano, and really in terms of nano, and then 10 to the negative 12th. You see me looking it up, and even I'm like, whatever. It's pico. The ones that we typically use on a regular basis, milli and micro. Nano, when we get to 214. 214 we'll use nano a lot. We almost never use pico. So on like the tests, it will be which is larger, a millimeter or a micrometer? And you just go millimeter. In the other direction, oh, we don't have this. I like this because that's deci. And it is just by lowercase d. So a decimeter is 1/10 of a meter, which brings up the word decimate. One team decimated the other. If you literally took it at its face value, then they killed off 1/2 of the team. So that's where the word comes from. Deci, 1/10, mate. I think it's some Latin or Greek term for kill or destroy. And so that's where it comes from. Over here, 10 to the 3rd kilo, K. We're familiar with kilo because we have kilobyte or kilobyte. Some files, like a letter or a picture, are in so many kilobytes. This is mega, capital M. Now, capital M, megabyte, it's what you're familiar with programs. Programs are so many megabytes, and they could even get as big as gigabytes. That's also the size of like your RAM. 10 to the 12th terabytes. 10 to the 12th, excuse me. And then it goes on to peta, exa, some other things, which is really, as far as the book says, the largest they have is 10 to the 24th. So they're even larger numbers than this. There was a push by a student. They filed a request of the numbers people, the people who are in charge, for naming 10 to the 27th. And they wanted 10 to the 27th. It's not true. They wanted it, I think it was capital H, which would be short for hella. Because if you have one hella meter, that's a lot of meters. So scientists are known for not being funny. They turned it down for some reason. So when you see kilo, mega, giga, tera, deci, milli, micro, nano, pico, you're dealing with powers to of 10 of whatever quantity is mentioned next. You could have a micro furlong. Oh, one last thing about time. A fortnight is 14 days. Just a standard unit of time when people were like, well, I gotta go from Berlin to Rome on foot. It's gonna take me like 4 fortnights to get there. They didn't have the Autobahn back in the 1500s. So the fortnight in furlongs gives me the best velocity that I could ever have, which is furlongs per fortnight, which is what you do in the homework. Now, What we're going to do next are conversions. And we're kind of on time. For conversions, what we effectively do is we take something and we multiply it by 1, and we still get that something back. All conversions do is change the units of a quantity to some other units. So in this case, what we're going to do is we're going to convert 3 yards to feet, which is very easy. You can just sit there and go, boom, 9. But let me show you how to do the conversions first, and then we can get more complex. We can do, one of the things that wasn't in the list of units, 3 yards, or 3 feet in a yard. Remember that. But 3 feet in a yard, we can divide both sides by feet, and we can get 1 is equal to 1 yard per 3 feet. We can divide both sides by yard, and we can get 3 feet per yard is equal to 1 as well. So those are expressions of 1. 1 times anything is anything. All that happens are the units shift. Well, let's do the conversion. I have 3 yards, and what I need to do is I need to multiply it by something so that the yards cancel out and are replaced with feet. So 3 yards times 3 feet per yard. Yard cancels, and I'm left with 9 feet. How simple is that? Now, I do understand that there is a subset of students who do their conversions a different way. But they write it out like this. Oops. That's fine too. I'm okay with that. I do it this way. You can do it your way. I don't judge. In this particular case, I'm fine with either way. Well, let's do now something a little bit more complex. Let's say you had 3 square yards. How many square feet do I have? So now, that one was linear, or length. This one is area. So if I took this 3 square yards, I would still multiply it by 3 feet per yard. But one of the problems that I have with this is that the units don't completely cancel out. One of the yards cancels with one of those yards, and I'm left with a yard foot. Well, that doesn't make any sense. So what you do is you multiply it again. So 3 times 3 times 3, or 27 square feet. And so that is an area conversion. The biggest mistake that people do is they don't do this. 3 times 3 feet per yard squared. This is how I typically write it out. 3 feet per yard, 3 feet per yard is 3 feet per yard squared. Now let's take a look at this. When you wrap it in a square, not only you square the number, you also square the units. A lot of people will write this down, fail to square the number, and then the whole thing just falls apart and they get the wrong answer. So really, you just take 3 times 9, 27, and that gives you an area conversion. The last thing we'll do, or we'll next to last, of this particular region. Is we'll do, well actually it'll be the last of the conversions. We'll do something, now that we've got a good idea about what's going on, I'm going to take 50 cubic meters per hour. Say you had a pipe putting out 50 cubic meters per hour. And I wanted to change that to how many cubic feet per second is that? So that's the conversion. And in fact, if you know how to do a problem like this, just as a side note, the test, when you take a look at it, there will be 25 multiple choice. There will be 3 full problems. And there's a problem called an appetizer problem. It's a problem technically, but it's a small, like an appetizer. Get your palate ready for the big ones. So this would be considered an appetizer problem. On your first test, you're going to have a basic conversion where you're going to do something with cubed or squared over a period of time. So for something like this, you have to be careful and do your conversions. The first thing that you can do is you can convert the time. 1 hour, 60 minutes. 1 minute, 60 seconds. Hour, minute, minute. Seconds are left in the denominator, so it is now a unit of seconds. Now I have to convert the meters. Well, meters to centimeters, 100 centimeters per meter. Meter is cubed, so I have to cube it. Centimeters to inch, 1 inch, 2.54 centimeters. Cube it, since I've got centimeters cubed. And then the last one, 1 foot, 12 inches cubed. So the time are all canceled out to seconds. Meters cubed, centimeters cubed, inches cubed, and I'm left with feet cubed. Now what I'm going to do, I typically don't do the next step, I just calculate it. But this becomes 50 times 1 over 60 times 1 over 60 times 100 cubed times 1 over 2.54 cubed times 1 over 12 cubed. This is so I can keep track of all the numbers. I would say when you're first starting out, do it like this, and then once you get a little bit more proficient, then you can do it this other way. And and it's helpful if I have people checking my numbers. Oh, it's almost like I planned. .49 cubic feet per second. Now let's talk about numbers in terms of the test. Technically, the number that I get is 0.4904814, blah, 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 blah. I don't want that. Keep it short. Keep it to just a few sig figs. I would probably, since it's 0.49, I would accept 0.50. That would be fine. 0.49 carried out to a few sig figs, that would be great. If you used 0.490, I'd be like, okay, fine, stop. But if you're doing that, that's just OCD-ish. That's not important. The other thing is, let's introduce myself. I'm the head of the School of Alphabet Soup Mode. You all are participants in the plug and chug method. I'm going to rip that out of you. It's for your own good. Look at what I did here. I did one calculation, only one opportunity for error. A lot of you would take that problem and use your calculator 4 or 5 times. Every time you run your calculator, you're introducing a chance for error. Also, if you round 3 or 4 times, you're introducing inaccuracies. That's why I'm not a big fan of sig figs, because I know that you're already plugging and chugging 3 or 4 times with a lot of cleaning going on, and that just makes it inaccurate. Understanding basic conversions is a fundamental need. After the first test, it's just expected that you understand how to do this. All right. Well, let's start doing some physics. Itty bitty. In my simplified state of Mississippi, first, that's Mobile, that's where my home is, or that's where my mom is, and that's all that matters. I-55 kind of runs like this. I understand it's a gross simplification, but that's what physics is. We simplify it and then we expand upon it. We have Memphis up here. This map should be learned because in one of the problems in your problem set, it's used. This is state line. Here is Jackson. Here is Oxford. So there's Memphis. One of the things that you notice as you drive to New Orleans or drive up to Memphis on I-55 is that the mile markers have a particular pattern. If you were to go north, do the mile markers increase or decrease? They increase, yes. We're going to get used to this. You're going to speak out in class. Now, for Memphis, what I'm going to do is simplify it and say it's 300. At mile marker 300, you are at Memphis. Now, granted, I think it's 302, but let's not get picky. Oxford, I know Oxford's not on I-55, but it's part of the problem. It is, what did I pick? I think it said 225 miles. And all of this is really showing position, like a number line. We're all familiar with number lines. In Jackson, it's 150. And in state line, it's 0. Now, 0 miles is the origin. You have to have an origin. You have to have a location that says everything is based on that point there. So if you're to the left of the point, you're negative. If you're to the right of the point, you're positive. In this particular case, everything is north. Now granted, if you go south of state line, the numbers jump back up to like, I don't know, 40 or something, because it only counts the distance within the state. One time I said, if you're standing at state line, which mile marker do you see? And someone said the less miles marker. And I was like, that's just genius. Did you get it? Les Miles, Coach LSU, Les, what was that? But it was funny at the time. Now he's been fired, so now it's not so funny. So we've got the origin. The origin lets you know this is 0. If I set Jackson as the origin, Memphis would be 150 and State Line would be negative 150. It doesn't really change anything except for the label. Now, there is a word which we call displacement. Question: you drive from Oxford to Jackson. What is your displacement? Now first we got to understand, well, what's displacement? In these number lines, you have to have a label for it, a generic value. In our mile marker situation, for our position, we're going to pick X. So if I said my X was 150, where am I? I'm in Jackson. If I said my X was 300, I would be in Memphis. That's pretty easy. There are several different ways of using, and you could pick anything. You could pick Y, you could pick A, you could pick a taco. But as long as you say taco is position, now granted, don't do that on the test. But if you said taco is my symbol for position, every time you use position, you draw a little taco. But we don't want to do that, so we use simple things like X. I am well, back when I was a grad student, I worked at SLAC, which is in California, and we have like 2,000 different physicists coming from all these different countries. And so physics has evolved, and physics is described and used different ways of expressing things. And this illustrates, some people use X1 is their initial position and X2 is their final position. Other people use X0 and X1. Other people use XI and XF. As long as you're willing to define what that is. And what we're going to do is initially we'll use this. When we get to motion, we'll use this. It doesn't really matter as long as you're willing to define what's going on. For displacement, the displacement is designated by a capital delta. Change in X is X2 minus X1, the final position minus the initial position. You're driving from Oxford to Jackson. The final position is 150. The initial position is 225. So this gives you minus 75 miles. Displacement can be positive or negative. Now, if I asked you the question, what's the distance between Jackson and Oxford, or you're driving from Oxford to Jackson, what is that distance? The distance is the absolute value of displacement, and it is always positive. So in this case, the distance d is the absolute value of negative 75. So it is 75 miles. Another thing that you notice when I'm doing problems, I love me some units. I believe in units. If you don't have units on the answer, we've got issues. But what you do with the units in the middle, that's just a waste of time, as far as I'm concerned. If you want to use your units to make you feel better during it, great. If not, that's fine too. Displacement, the change in position. Final minus initial. That's how I remember it. Distance is just the absolute value of that. There is concept of velocity. If it took 3 hours to get from Oxford to Jackson, what is your velocity? And that is a mutant U. The definition of velocity, and actually I should be more precise, your average velocity. If you're dealing with average of velocity, it is V bar. There is a line written above the V. That average velocity is your change in position or displacement divided by the change in time. So your average velocity is negative 75 over 3, or negative 25 miles per hour. Average velocity can be positive or negative. When you have average velocity, there's something called speed, or average speed. S bar, average speed, is equal to the absolute value of average velocity. So your average speed is the absolute value of negative 25, which is equal to 25 miles per hour. Average speed, always positive. So while we're absorbing this, a little thought experiment. No, it's not a thought experiment, it's a challenge. I've never had anyone do this. I would applaud you. If you did, I wouldn't say you were my student, but I'd go, yes. Get in your car. Make sure the cops are on the road when you do this. Put your car in reverse. And gun it. Gun it as fast as you can. Gun it right down 6 and just go yeehaw right by the cops. And then when the cops pull you over and they go, we saw you doing 70 miles an hour, you broke the speed limit, you go, no, officer, I'm innocent. I didn't break the speed limit. Exactly. I was going in reverse. So I was actually going negative 70 miles per hour. You can't dare you to arrest me. What's wrong with it? What's wrong with the logic?
Have negative speed.
You can't have negative speed. Speed is an absolute value. So technically you were traveling 70 miles an hour. And when I presented this question on Twitter, the police said, not only is it breaking the speed limit, You're also doing like reckless endangerment, all sort, and they listed like 4 or 5 other offenses, and I was like, okay, we won't do that. But it's a good thought experiment. Now, there is the idea of average speed and instantaneous speed. When you look in your car, there is a gauge. Does it read your average speed or does it read your instantaneous speed?
Instantaneous.
It's the instantaneous. Your speedometer gives you your speed at that particular moment. If you're going really fast, it's over to the right. If you're going really slow, it goes close to 0. Average speed is this. The macro change in position over the macro change in time. Instantaneous speed, and we'll call instantaneous speed, it's the same difference as average velocity and instantaneous velocity. For speed, it's delta x over delta t. Same with average, actually this should be used as average velocity. Because I'm going to get away from speed soon. So the average velocity is the macro change in x with respect to time. Average speed is the absolute value of this. Instantaneous speed is the absolute value of this. Velocity is dx dt. V bar is delta x over delta t. Delta x is, over the course of the trip, I traveled 3 miles in a minute. So my average velocity was 3 miles per minute. But your instantaneous speed is, as I'm walking and I freeze time, I have a velocity value at that particular moment. When you're driving to Walmart, you don't drive a consistent speed. You speed up, you slow down, you come to a stop. It changes with time. That is instantaneous speed. Now, for all of this, we have position, which is x. At a particular time t, you have a position. And then you have velocity. And v is dx dt. So if you have a particular velocity at a particular moment, it will be a v. Then there's the same deal as if you can have average acceleration and average acceleration and instantaneous acceleration. We deal with instantaneous acceleration. Which is just the change in velocity with respect to time. You can use, I think we do have, average acceleration is the final velocity minus the initial velocity or change in time. Now, there are, once again, some people could ask, well, what's the change in acceleration with respect to time? When we get to in 213 and 214, we don't test on this, but this is for your pure benefit. By definition, the change in acceleration with this respect to time is called the jerk. Just that pull. Now, here's another reason why scientists aren't very funny. There is in America, like 213, you don't cover this. But if you decide to become a mechanical engineer or something where you got to figure out all this different stuff, the change in jerk with respect to time is called a snap. The change in snap with respect to time is called a crackle. No lie. And what do we think the change in crackle with respect to time is? Pop. In Europe, they don't use these because they're not funny. And they don't even like the fact that Pluto's a planet. So in this, we won't be covering it, but it's a good thing to talk about. And if you just mention, oh, hey, jerk, and they go, what did you say? I said, oh, I was commenting on your change in acceleration with respect to time. Hopefully that'll get you out of it. In these motion equations that we use, position, velocity, acceleration, these are going to be what we're talking about for the next day or a couple of days. Position, velocity, and acceleration. Now, acceleration is not always what I'm going to say right now. Acceleration can change. Like I could start speeding up. I could come to a stop. I could slow down. I can accelerate in a different direction. But in terms of the problems that we're doing, acceleration will be 0 or non-zero, and both are constant. You're going to have an acceleration in 213 that I know there are problems where it changes, and if there are problems, I will make you aware of them. But I keep things simple. Why? Because this is your first day of physics. Acceleration for an object will always be 0, or it will always be non-zero and constant. So if it is 0 at the beginning of the problem, it's 0 at the end of the problem. If it is negative 9.8 meters per second at the beginning of the throw, it's 9.8 meters per second at the end. It does not change. Velocity, now there are derivations for this, but we'd have to know calculus. Velocity is expressed as, this is the velocity v at time t. Velocity v at times t is the initial velocity plus at. Final velocity, initial velocity, acceleration, and time. The position equation, x equals x naught plus v naught t plus 1/2 at squared. Typical plots for acceleration. The acceleration will either be non-zero and constant, or 0 and constant. It could be up here, down there, either way. For velocity, when you look at this, this is a linear function. That's a linear function. Now, granted, linear could mean this, could mean that, could mean this, but in each of those cases, it's linear. Also, another definition of what linear is, linear means that the slope never changes. Slope here to there is the same. Slope there and there is the same. Slope there and there is the same. For position, we're quadratic. or bowed or curved. Now this thing, depending on the situation, normally it could look like this. It could do these weird bow things. It doesn't always have to stay above the line. It could go down. If A is equal to 0, it's linear, which means then you can get the typical flat, rising, stuff like this. This is Dr. Eschenberg's favorite equation. And when occasionally I break into tutor mode, and the tutor asks you, Dr. Eschenberg said that it was his favorite equation, and you go, yeah, then write it down. It's probably among the most important equations you need to know. This is my second favorite equation. So it lets you know how velocity is as a function of time. 20 minutes. So what we're going to do is a quick demonstration for the next 5 minutes of various Everything on the first row is position. Everything on the second row is velocity. All the horizontals are functions of time. And there we go. Now, I need an origin. Let's say the origin is the line running down the middle of the room, level with the camera. So the first thing I'm going to do, everything to the left of you, negative. Everything to the right, positive. So the first thing I'm going to do is this. Begin. Stop. Now, what was my position? It was negative, yes. And once again, this is not Jeopardy. Don't ask it in the form of a question. I was to the negative. So my position was negative and what? What quality? Constant. So the x looked like that. In fact, what did I do wrong? What's wrong with this?
It should be below the line.
It should be below the line. Yes. What was my velocity during the motion? It was 0. You can also tell by the fact that, what's the slope of that line? It's 0. So if the slope's 0, the value of velocity is 0. What's my acceleration? It's 0 as well, because the slope of velocity is 0 as well. Now for the next one, we will do simply this. I moved from the left side of the room to the right side of the room. So what did my position look like? It started negative and it went that way. Does it have a slope? Yes. Positive or negative? Positive. So it has a positive slope. Does the slope of the line change? No. So the velocity looked like that. What's the slope of that line? 0, which means the acceleration is 0. So you can look at the lines and tell what's going on. Now for the next one. Now I can't do the whole thing because it's a small room. But let's say begin. Stop. Y'all want me to crash into that? Ooh. So what did my position plot look like? It bowed. At the beginning, was my velocity slow or fast? It was slow. So probably the best thing to do, or actually, what's wrong with that? I had an initial velocity of 0, and then it increased like that. That has a slope, which means it has a non-zero and constant acceleration, which means the acceleration looks like this. The position, I started on a negative side, so my initial position is there. Had I drawn this down there, I would have a negative velocity, which would be nonsensical for the motion. And here, the value of velocity is close to 0, which means that the slope of the position line is close to 0. But as time progresses, it increases. So it bows upward. The slope here is greater than the slope down there. And now for our last, I don't want to trip over the cord and I don't want to smash into the iMac. All right, the last one is this. Now what did I do? Well, it looked like a fool, but that reinforces the learning process. I started negative. I had a high positive velocity. With time, as I got to this point here, I came to a stop, and then I began going backwards faster and faster. Which means that I had a negative slope the entire time. Here, it was negative. At the beginning of the motion, I was running fast, but slowing down. Here, I'm running slower, and then on my way back, I was speeding up. In all cases, my acceleration was backwards. My acceleration was that way. The position looks like this. Like you're throwing a ball up in the air. Initially, I had a high velocity, high speed. The slope of this line is high. As I got to that side of the room, my velocity was 0. And the slope of that line is 0. As it increases, it comes back down. But with a greater speed, so an ever-increasing slope in the negative way. And here is my acceleration line. At the beginning, the value of acceleration was the negative value. At the highest point, where I came to a stop right there, that acceleration was still that value. And as I was coming down, it's still that value. The acceleration, remember, I'll be quizzing, well, not quiz, but asking you questions tomorrow. At the beginning and at the end and at the middle, acceleration was a constant, a negative value constant. So you need to remember this. 10 minutes. No, 13. Yay, 13. So let's do a simple problem. I'm watching the time. So a car accelerates from rest at positive 4 meters per second per second. It races over, hold on, I need to, we're doing our first problem. It does this acceleration from rest at 4 meters per second for 10 seconds. What is its final velocity? And how far did it go? What is its final position? It is a classic one-dimensional motion problem. It is something that if you got this on the test, you'd be like, done, give me my points. It's a 1D motion problem. And really what I'm doing is going over a very simple topic, introducing the concepts of problem solving. It's a 1D motion problem. What should I do first? Write down my 2 favorite equations. Now, I have said before, not a big fan of numbers. Don't like plug and chuggers. And then one year, a student said, actually, it was in this room. He said, you do have a favorite number. I was like, how dare you, sir? What is it? And he goes, your favorite number is 0. And I go, fair point. My favorite number is 0, and I'll tell you why. When you draw this thing out, here's the start, here's the finish. That's my distance x. At this particular spot, there is a velocity. Whenever you do problems like this, you need to first identify the origin. Where is the best place for an origin? Start position. This is where x naught is equal to 0. If you say the origin is at the start line, you know for a fact that x naught is 0. So, that's 0. I do love me some zeros. The next thing is, you look at this problem, there's another 0 wandering around. What's that other 0? You can speak up. Fill the room. The initial velocity. Now I'm going to take credit for her because she said it louder. Fill the room. It's okay. What do you want to be? Just curious. Yeah. A nurse. So I've been in an emergency room. I was trying to pass an 8-inch millimeter hunk of glass through my urethra. I had a kidney stone. I don't want a nurse to go, no, you want someone going, I'm going to take care of this. Here's some morphine. Hope you feel better. Which it works. It starts from rest. Initial velocity is 0. Why? Because it started from rest. It won't always start from rest, but in this particular case, it does. Now, the next thing is ID what you know and don't know. Do I know the final position? No, I don't. I put little red bars under things that I don't know. I know acceleration. I put little green bars below that. I know my time. I know that. I know my acceleration and time, but I don't know my final velocity. Here, I have 2 equations. One only has one unknown. The other has only one unknown. So I could solve for these variables right away. So rewriting them, I get 1/2 AT squared and AT. So X becomes 1/2, 4, 10. 4 divided by 2 is 2. 2 times 100 is 200. A is 4. T is 10. So this is positive 40 meters per second. And that solves the time. Now, just reiterating, going over, physics problems are very easy to solve if you have just the basic understanding of how to problem solve. First, just read the problem, and as you're going, car accelerates from rest, stop, V0 is 0, at +4 meters per second, stop, A is +4, does this for 10 seconds, stop, time is 10. Draw it out. Put the initial position as the origin. Plug in your zeros. ID what you know and don't know. And then see what drops out. That's the initial part of problem solving. All right. I can't do the next problem. What we're going to do tomorrow is one-dimensional motion, finish with that, vector addition, and 2D motion. So it'll all cover the same thing. Real quick, the 5 o'clock lab is led by our best TA. We're making the pitch for that. If you want to transfer into the 5 p.m. today, go to the 5 p.m. But before that, after lunch, come find me and we'll fill out your add drop form. If you're on the waiting list for sections 1 or 2, go to those sections and we'll see what we got. I'm not transferring people into section 1 or 2, but I will definitely pull them out and put them into 3. If you're scheduled for 1 and 2, go to that today, and then once I get the sign-up sheets for my TAs, we'll talk about who gets to stay tomorrow. We swipe tomorrow, and after tomorrow, we never swipe again. Thank you.